Welcome to video number 8 in the Fortitudo.tech Python package walkthrough. In this video, we'll be going through an example that implements entropy pooling views on risk factors, such as interest rate curves and implied volatilities. Until now, we have implemented entropy pooling views on returns directly, but entropy pooling is actually much more flexible than that and works on risk factors also. As usual, we start at the front page of the repository and then navigate to examples. And here you see that example number 7 is called risk factor views. This example is not the accompanied code to any article, but it refers to the entropy pooling article to give you an understanding of how we build this matrix R that can contain both returns and risk factor simulations. So as usual, we import the packages that we need, and then the first thing we do is to take the time series data that we have been going through in an example before, load it in and transform it in a way such that it has nice statistical properties. So in econometrics language, it would be transforming to something that looks stationary. So here we start with equity. And in this case, this is just a log return instead of having the price series directly. So most statistical models, they work best when you have data which is stationary, and I'm quite sure that you have learned this in your econometrics courses. So with the zero coupon curves, what we can do is to compute some discount factors, and then basically this is the price of a zero coupon bond. So if we use these discount factors with a constant maturity and do some log changes in them, then we also get this nice time series that looks stationary. So if you do some eyeball econometrics, then you see that this at least does not look to have any trend or anything like that. For interest rates, it's probable that they are stationary already, but the values might be highly persistent, making it harder for some statistical models to learn. So it's really up to you if you want to do this transformation or not. This is just one suggestion that we have. The important point is that when you make these stationary transformations, then it should be easy for you to come back to what you actually want. So in this case, you should be able to compute the zero coupon curve, because this is what we'll be using for pricing bonds. So here, when we look at the volatility time series, well, we can just take the log difference in the volatility time series, and you will have this nice looking stationary data. For the credit spread, we perform the same transformation that we do for the zero coupon bonds. So of course we can't really interpret it as a zero coupon discount factors in this case, but it doesn't really matter if we have this economic interpretation or not. The only thing that we want is just to do some feature engineering such that our data becomes easy for us to work with. It's similar to when you input some data into machine learning models, then you would usually standardize it. So you can see all of this just as a part of the feature engineering that you need to do to make it easier for your models to learn from that. And then once you have these stationary transformations, you project them into the future, and then you go back to the risk factors that you need. So this would be equity prices, interest rate curves, credit spreads, and implied volatilities. Okay. So once we have these stationary transformations, we can just look at them and see what is the historical daily return distributions for equities, for example. So of course, using the historical data, this is perhaps one of the most simple risk modeling approaches that you can take. So in real world applications, we recommend that you do something else, where you use the stationary transformations to generate entirely new paths. Yeah, there are some recommendations for what you can do here. You could also use this exponential decaying probability if you want, but this is still quite simple compared to what is possible. But here you can see that how we use the stationary transformation to go back to the equity P&L. It looks like this. And in the same way that you can generate the equity P&L, you can generate a distribution for the zero coupon curve based on these historical scenarios. So this is what we do here. For the implied volatility surface, because it is three-dimensional, then then it's hard to visualize the distribution. But here, this is just one index from the historical simulation, where you can see how the volatility surface look. If you want to see the distribution, you can perhaps loop over this plot, and then you will be able to see how the volatility surface changes. Finally, here we show a distribution for the credit spread over the next day. Alright, so now we have our risk factor simulations at hand, and now we want to price some assets. So in this case, we assume that we can invest in the equity index, that we have a zero coupon bond, and that we have some credit bond, and finally that we have a put option written on the equity index. So here for the pricing, a lot of things happen here. So it's I think there's no way for you to go through around you going through all the details to look to see what you understand. But basically here I just make some coupon payments for the zero coupon curve, and then I add the final payment at the end. So here I assume that the coupon payments are free, and then the same thing for the credit spread, that it's free on top of the zero coupon payments. So here you can see that I compute the government bond prices, and once I have the prices, then I can use these simulated interest rate curves or discount factors to compute a government bond relative P&L. So this is just the return in this case. It's the same thing here for the credit bond, and then here for the put option it becomes a bit more complicated than that. But let's see if we can figure it out anyway. So the first thing for the put option, we of course need to know what the forward price is today, and we would need to extract the implied volatilities and zero coupon rates. This is just to get the initial price. So after that, we want to generate some simulations for the put option also. So in that case, we would need to simulate the forward price, we need to simulate the implied vol surface and the interest rate changes, because the time to maturity, of course, we could make some adjustments there. We make some simplifying assumptions in this case to avoid interpolating between, let's say, the 1 month implied volatility and 3 month implied volatility. So this extra day that we have, where the maturity of the option is a bit shorter, we ignore that part to make things easier in this case. But the pricing differences should not be significant in the simulations anyway. Alright, so here you can see that we compute this put relative P&L, and we make a plot where we verify that it looks like a put relative P&L. So here you can see we have the relative P&L of the equity index, and then we have the relative P&L of the put option. So since this is an at the money forward, then the delta of that option should be around 50%, around at the money here. And then of course you would have some convexity. So here you can see that there is some slight indication of convexity, but apparently the moves are not that large. At least what you can see from this here is that it's not a entirely linear relationship, because if it was a linear relationship, then here where you have an increase of around let's say 9%, then you would have the similar thing here for the put relative P&L, but you can see that it's much lower. So definitely there is some change in the delta of the put option in this case. Alright, so now we have simulated the risk factors, we have priced some instruments, and now we want to combine it all into one matrix, so we can use that matrix to implement entropy pooling views, as we talk about in the entropy pooling article. So this is what we do here. Basically we do the simulated zero coupon curve, implied volatilities, and then credit spread also, and then add it to the P&L simulations that we have, because now we can just implement views on the risk factors, and then we can see what happens to our P&L immediately. Alright, so here we implement some entropy pooling views, and of course the first thing we need to do is to ensure that the probability sum to 1. After that, the views that we implement is that the 1 month zero coupon interest rate increases by 2 standard deviations, while the implied volatility 1 month implied volatility increases by 1 standard deviation. So of course this is just some examples that I came up with, that I thought were interesting to look at. So here, you can go through these views to see that this is actually what I specify, and then finally we just input the things that we need to the entropy pooling function to compute the posterior distribution, we just verify that it's calculated correctly according to the views here also. Okay, so in this case, of course, we could plot a posterior and prior zero coupon curve distribution, but in that case, I think it would be very hard for us to see the difference, and there will be many curves. But if you want, you can try to do something like that on your own. So here I just plot the average zero coupon curve that we have in the posterior distribution and in the prior distribution. So this is how it looks, and you can definitely see that it seems that there's happened something to the interest rate, that this has increased. But not only is it the 1 month interest rate, it's over the entire span of maturities that we have here. All right, so now we just need to specify a portfolio and then compute its P&L. So here you can see that we have a portfolio where we assume that it has 30% equity exposure, and then we are hedging this equity exposure with the put option. So for the exposures, we just specify them, and then for the weight of the puts, we of course need to know what is the market value of this exposure that we have. So basically the credit exposure, that's going to be the remaining that we have left for the weights, and then we collect it into this exposure vector, so we can verify that if you look at the exposures and then the weight of the put, so exposures of all the other cash assets and the weight of the put, then it's going to sum to 1. And this is the self-financing constraint that we have from this portfolio management framework for derivatives. Okay, so here we just compute the portfolio's P&L, so we can analyze it and see how it is affected from the risk factor views that we have implemented. So you can see here that the first one we plot, this is just the prior, and then we just specify that the weights in the posterior need to be the posterior probability vector. So you can see that for the return distribution we have here, if we assume a scenario where rates increase and implied volatilities also increase, then it seems that we will have a loss in our portfolio, which I believe is quite plausible given the dependencies that are in this simulated data. All right, so this is the end of the 7th example, and as always, if you like these videos and if you like this package, then I encourage you to give the GitHub repository a star, and then I hope to see you in the next video.